All right, welcome back to the Deep Dive. If you've been paying any attention to the world of AI, you know that large language models like GPT-4 and Llama are doing some pretty incredible things with language,
Absolutely incredible. Writing, summarizing, chatting.
like very, very smart machines.
And their power really comes down to how they process text, these sequences. But there's a bit of a catch, isn't there?
There usually is.
Yeah, for all their power, they often hit a wall, a big one, when the text gets really long.
Really, like you mean like trying to read a whole novel to answer one question, or a massive legal file?
Exactly that. Stuff that's way, way longer than what they usually see in training.
Okay, why? What's the core problem there?
It comes down to the heart of the transformer architecture, the self-attention mechanism. It's amazing, lets the model weigh the importance of different words,
What?
but its computational cost and the memory it needs just explodes. It scales quadratically with the sequence length.
Quadratically. Okay, let's break that down. Double the text length.
4 times the computation.
Triple it.
9 times the work. Yeah, it ramps up incredibly fast.
And that's what creates this hard limit on the context window, how much text the model can actually look at, especially during training.
Precisely. Now, people have tried all sorts of clever things to get around this.
Like what? Approximations.
Yeah, approximations like sparse attention or low rank methods. Some use sliding windows, others try adding external memory.
But these aren't perfect solutions.
They often involve trade-offs. You might lose some efficiency, or they don't integrate quite right, or maybe they struggle to capture those really crucial connections between bits of text that are far apart.
Right. So handling truly long sequences efficiently and without losing understanding is still a huge challenge.
A major frontier, yeah.
And that brings us nicely to our source material for this deep dive. A recent paper from Yale University proposing, well, a pretty different way of looking at this.
That's right. They call their approach attention tensorization.
Attention tensorization. Okay, so our mission today is to unpack that. What does it mean? What's the innovation here? Because it sounds quite different.
It is quite clever.
And crucially, does the paper show that it actually works? Let's find
Let's
out.
dive in.
Okay, attention temporization, the core idea.
Mm-hmm.
It seems to start with rethinking how we even structure the input, right? Not just a flat line of words.
Exactly. Instead of that 1D sequence, they propose reshaping it. They tensorize it, turn that long line into a higher order tensor.
Higher order tensor, like folding the line of text into a grid or a cube.
You got it. Imagine folding it into a multidimensional shape. Could be 2D, 3D, even more dimensions.
Okay, folding a line into a cube. What's the intuition there? Why do that?
Well, think about distance. In a long line, two related ideas might be hundreds of words apart.
Right, very distant.
But if you fold that line cleverly into, say, a cube, those two words might end up much closer together in that 3D space, maybe on adjacent faces or nearby inside the structure.
Ah, so you're reducing the effective distance.
Precisely. The paper has this neat visual. A distance of 12 in a sequence becomes just 5 in a simple 3 by 2 by 2 tensor. Suddenly, interactions that were out of reach for standard attention might be right there locally in the tensor.
Okay, that makes sense spatially. But it's not just about reshaping the input, is it? They change the attention mechanism itself.
That is the absolute key. It's not just applying old attention to a new shape. They introduce tensorized attention,
Tensorized attention.
which replaces the standard vector and matrix math with equivalent operations designed for these multidimensional tensors.
Okay, how does that work? How does it process information across this cube of text?
Instead of trying one massive calculation across the whole folded structure, it works dimension by dimension, sequentially,
Dimension by dimension. Like it looks at connections along the rows first,
then along the columns.
then maybe depth-wise if it's a cube.
Exactly. It breaks down that huge, complex 1D interaction problem into a series of simpler, more localized interactions within the higher dimensional tensor space. It's a really fundamental shift.
That feels more structured somehow, like processing rows, then columns. And they actually built custom code to make this run fast.
Yeah, they mentioned using an efficient custom Triton kernel, essential to make the theory practical.
Okay, reshaping the input, redesigning attention for tensors, processing dimension by dimension. Very cool. But why go to all this trouble? What are the big claimed benefits?
Two main things, and they're connected. Much better computational efficiency and, potentially, a more powerful way to model the structure in the data.
Let's hit efficiency first. That quadratic cost is the big killer, as we said.
It really is. And tensorization, according to the paper, offers a huge improvement here. Theoretically, they show it cuts the complexity down from that painful n being sequence length down to O n log n.
Okay, for anyone not deep in complexity theory, that's much, much better than n squared, especially when n gets large. The cost grows way slower.
Massively slower, and they back this up with practical results. They took models like Llama 8B, originally trained with maybe an 8K context,
Yeah,
adapted it with tensorization, trained it efficiently up to 32K context,
okay.
and then showed it could run inference, so actually process text on sequences up to 128,000 tokens.
Whoa, 128K from 32K training.
Yep, and get this, with an 11 times speedup compared to using optimized full attention for that same 128K sequence.
11 times faster inference at 128K tokens. That's genuinely transformative for dealing with huge documents.
It's a massive practical difference, so efficiency is a huge checkmark.
But you said there's more, something about modeling power.
Right. The paper argues that this temper structure isn't just a compute trick, it actually helps the model capture dependencies better.
How so? By forcing this dimensional processing.
Kind of. By structuring attention this way, it effectively creates what they call a multi-hop attention process.
Multi-hop.
Yeah, instead of trying to make one giant leap between two distant tokens, the connection is formed through intermediate steps, hops across the tensor dimensions.
Oh, like information passing through different layers or parts of the structure.
Exactly. It builds up connections hierarchically, local interactions first, then interactions between those local groups, and so on. It allows the model to capture relationships at different scales more naturally.
That feels quite intuitive, actually. Building understanding layer by layer. The paper also got a bit technical, talking about low-rank structure.
It did, but the core idea is actually pretty neat when you represent the attention patterns as this multi-dimensional tensor.
Yeah.
And it turns out that structure is inherently more compressible or simpler in a mathematical sense. It has a more pronounced low-rank structure than if you just view it as a flat matrix.
And low rank means you can approximate it really well without needing as much information, less data, fewer parameters.
Exactly. You capture the essential connections more compactly. The taper shows empirically that their tensor representation needs way fewer parameters to hold the same crucial relational information compared to the standard approach.
So the structure isn't just faster, it actually makes the attention itself more informationally efficient.
That's a good way to put it. They even have a theorem backing this up, theoretically showing why this tensor view leads to that efficient low-ranked property.
Wow. Okay, that connects the structure and the efficiency gains on a deeper level. What about positional information? How does a token know where it is in this cube?
Good question. They adapt positional encoding too. Instead of one number for its place in the line,
It gets coordinates.
basically, yeah, a position vector with coordinates telling it where it sits along each dimension of the tensor. They use a tensorized version of rope rotary positional encoding.
A position vector. Makes sense for a multidimensional space.
And this hierarchical positioning is apparently key to their length extrapolation results.
How so?
Because you can potentially extend the sequence length massively by just extending the positions along one dimension while keeping the positions in the other dimensions within the range the model actually saw during training. It's a clever way to handle unseen lengths.
Okay, so there's some solid thinking behind why this should work well for long sequences, both computationally and structurally. But theory needs proof. How did tensorized attention actually do in their tests?
They ran a lot of experiments. Seems pretty thorough.
First up, could they actually train models effectively on longer sequences using this?
Yes, they showed they could take existing models, OpenLlama, Mistral Llama, and continue training them efficiently on much longer contexts, up to 32K tokens in these tests, significantly beyond their original training limits.
So it works for enabling longer context training. Good start. Did it hurt performance on regular tasks?
That's crucial, right? And no, it seems not. On standard NLP benchmarks, common sense, world knowledge, reading comprehension, the tensorized models performed comparably, sometimes even a tiny bit better.
Okay, so efficiency doesn't cost you core capability.
Doesn't seem to.
But the real test is long stuff. How did it do on benchmarks designed for long context?
Right, they tested it on Long Bench, and it performed well across those tasks that really require understanding relationships across thousands, even tens of thousands of tokens.
And efficiently.
Yes, crucially, it was significantly faster than full attention on these long tasks. They quote something like 0.61x the average running time. So faster and effective on long inputs.
Okay, that's compelling. What about that zero-shot extrapolation you mentioned, going beyond the training length?
This is probably one of the most eye-catching results. Models trained with tensorization on 32K sequences
Yeah.
could directly process sequences up to 128K at inference time.
With no extra training just for extrapolation. Straight from 32K training to 128K use.
Exactly, zero-shot extrapolation. And they compared it to other methods specifically designed for this, like PI, yarn.
And how did tensorization stack up?
It often achieved lower perplexity, especially for the Llama 8B model they tested extensively. Lower perplexity means the model is making better, more confident predictions on these super long, unseen sequences.
Better performance and that incredible efficiency gain you mentioned earlier, like 0.09x the time at 128K.
Exactly. It's that combination of effectiveness and speed during extrapolation that's really impressive.
Is this tensor idea just for language models or is it broader?
They suggest it's broader. They show results applying it efficiently to time series modeling
Okay.
and also fine-tuning other types of models like Roberta on standard NIP tasks, again showing efficiency gains. Suggests the core concept is pretty general.
Though they probably had to figure out the right way to fold the sequence, right? The tensor shape must matter.
Oh, absolutely. They mention that choosing the tensorization strategy, how many dimensions, the size of each, does impact performance. You need to tailor it. Makes sense.
This has been a really interesting look at a fundamentally different approach. So if we boil it down, what are the main takeaways for listeners?
I think the biggest takeaway is that tensorized attention genuinely seems to offer a new path around that quadratic bottleneck for long sequences. By rethinking the structure using tensors for both input and attention, they get significant efficiency wins.
Wins that enable much longer training context, and maybe even more importantly, that impressive ability to extrapolate to unseen lengths.
Right, and it does this while keeping performance strong on standard tasks. The core innovation is moving from that flat 1D sequence view to a multidimensional tensor perspective.
Capturing hierarchical relationships, leveraging that low rank structure, it just seems more efficient computationally and informationally.
That's the essence of it, rethinking the geometry of attention, really.
So this paper makes a powerful argument for the benefits of tensor representations in sequence modeling. It really makes you wonder, if this shift helps so much for sequences, what else could we unlock by thinking more deeply about tensor operations in neural networks?
Exactly.
Could this be a stepping stone for handling other complex structured data, maybe multimodal inputs or graph data, or even, high-dimensional scientific simulations? Is thinking in tensors beyond just vectors and matrices a key to the next level of AI?
That's a great question to leave people with. This work certainly hints that exploring the power of tensor mathematics within neural networks could be a very fruitful direction for tackling bigger, more complex data challenges ahead.